Hello, welcome to this video. So in this video we're going to be looking at what is quantum field theory and why we should care about quantum field theory. I'm doing this video as a video that sounds by itself, but it is also a good introduction to the subject if you want to look at my series of videos where I go through a book on quantum field theory and give an overview of the key concepts found therein. But I want to make this video to explain what quantum field theory is and why we should care about it. So, firstly, if we break down the word quantum field theory, we have the word field within it, and one could ask what we mean by a field. One might be used to things like gravitational fields and magnetic fields, and those are fields associated with forces. Whereas the kind of fields we deal with in quantum field theory are fields to do with particles, but some of those particles do also relate to forces, particularly particles called gauge bosons. But a field is kind of something that exists within space-time. You can kind of think of it as a fabric within four-dimensional space-time which can change its shape, and the field is continuous in this space-time, and space-time comes from special relativity. And then in quantum field theory we unite the formalism and covariance described in special relativity with ideas in quantum mechanics. And the way that we do this is we take a classical field and we then quantize this field by replacing our description of the field with operators. And these operators cause the field to be quantized in the same way that the replacement of classical variables to operators combined with the eigenvalue equation causes variables to become quantized in non-relativistic quantum mechanics. So the word quantize is perhaps slightly wrong. We're really doing something that in its non-relativistic counterpart would count as traditional quantizing. In quantum field theory, we're taking the abstract of quantizing. That is, we're doing something that represents quantization in non-relativistic quantum mechanics, but really it should have its own name, although there are certain advantages of thinking of replacing variables with operators in quantum field theory as quantization. And then the next thing to look at is why should we care about quantum field theory? Well, it's been proven that it describes the standard model very well. It describes it brilliantly in terms of experiments and what we actually observe. It describes the nature of particles. It describes the cross sections involved in particle interactions, and so it's hugely useful there. And also, if you're interested in quantum gravity, where we're trying to get to a theory of understanding space-time at a smaller scale, such as close to the Big Bang or near the apparent singularity of a black hole, then you'll probably want to use, at least at times, string theory, because string theory is one of the main contenders for a theory of quantum gravity, the other main contender being loop quantum gravity, although there are many contenders. But string theory is very popular, and also string theory is really nice because it describes particles but has some new features that we get when generalizing quantum field theory to account for the possibility that particles might actually be more like strings than point particles than we previously thought. So we have to change our equations of motion to account for this extended nature of quantum particles. And the last reason why is that quantum field theory can be applied to curved space-time even without a theory of quantum gravity. And when we do this, we get pseudo-answers. That is, we get answers which tell us about the universe. However, we're kind of cheating because we're not taking into account the quantum nature of space-time. We're just amending our equations of quantum field theory to account for the different metric due to the curved space-time. And so we are getting answers, but we know that there is more to the picture that we don't quite have yet. Applying quantum field theory to curved space-time has resulted in a lot of successes, including Hawking radiation and the concepts of black holes evaporating over time, but over a very, very long period of time indeed. So these are reasons why quantum field theory might be of interest. As I say, if you like quantum field theory, please check out my videos on quantum field theory for the gift of diameter, if that is something that you would be interested in. But I hope this video has given a good overview of what quantum field theory is and why we should care about it.